Hello, and welcome to a special edition of Linear Algebra in the Morning. Anyways, this is a cool video because this is the first time I get to use my new microphone. So hopefully this will clear up any sound issues with the sound being unclear or ruffling next to the computer. This will also mean, hopefully, I get to talk while I'm writing on the board and actually be heard. So I will say I'm getting used to the mic. I've done a few test runs to see how the volume works. And so I'm actively trying to make sure I don't talk too loud as to not overload the microphone. But I do apologize early on. I'm going to try my best to remember to talk I'll try to best to remember that the microphone is picking me up and that I don't have to speak loud enough to be heard by a computer. So in this section, we are going to talk about matrix factorizations. Well, one matrix factorization in particular. And so matrix factorizations work a lot like how we factor polynomials or numbers. So, we factor a polynomial by breaking it up into, a product of different polynomials. And we factor a number in the same way. And so these factorizations can have many uses. And so we do the same thing with a matrix. So a matrix factorization is just rewriting a matrix as a product of two or more matrices. And so we're going to introduce one special type of factorization and talk about why we like it. So first off, I want to introduce this definition. We say that a square n by n matrix is lower triangular if all of the entries above the main diagonal are equal to 0. So I think the reason for calling it lower triangular is that if you look at the shape that the zeros are making here, notice the zeros sort of make a triangle shape. And so we actually then have an equivalent definition for upper triangular, like that, where here the zeros just lie below the main diagonal. So lower triangular, all of the non-zero entries are lower. Upper triangular, all of the non-zero entries are upper. So you can tell the difference between upper and lower triangular based on where the non-zero entries are, not the zero entries. So given these two definitions, we're going to introduce our matrix factorization for this chapter. So we say that if A is an n by n matrix, and so notice here in particular, this factorization does not require A to be a square matrix. And suppose we can reduce A without row swaps. So a lot of matrices do require some row swaps to reduce, but we're going to introduce sort of this idea without row swaps first, and then we will generalize it at another point. We can factor A into the product of two matrices L and U, where here L is an m by m lower triangular matrix. So L is a square matrix with the same number of rows and columns as A has rows. And U is a row echelon form of A. So very important distinction here. U is a row echelon form of A, not a reduced row echelon form. So we're used to just completely reducing A all the way down to reduced row echelon form. But for the purposes of what we're going to do today, we'll only need the row echelon forms of A. And so then also notice U will have the same dimensions as A. So U is an m by n matrix as well. And so if we can do this with a matrix and write A as this product of L and U, we call this an LU factorization. So notice L, I think, gets its name from being a lower triangular matrix. So that's why we say L. Important distinction here. This always confuses me a little bit. U is not necessarily an upper triangular matrix because notice the definition here requires these matrices to be square. And so just sort of keep that distinction in mind. L is a lower triangular matrix, but U is just the row echelon form of A. Might not technically be an upper triangular matrix. So let's see what one of these things looks like. All right, so we're going to let A be the following matrix. We're going to define A to be a 3 by 3 matrix. 3, -7, -2. -3, 5, 1, 6, -4, 0. We're going to let L equal 1, 0, 0, -1, 1, 0, 2, -5, 1. And we're going to let U equal 3, -7, -2, 0, -2, -1, 0, 0, -1. So, is this an LU factorization of A? Well, so the answer is yes. It wouldn't be terribly hard to verify that U is an echelon form of A. I think you could do that with at most 3 row operations. Yeah, so we can quickly do that. So if we start with A here, so I'm going to just show that we can reduce A to U to show that A is in fact a row echelon form of, or U is in fact a row echelon form of A. So I'm going to do row 1 plus row 2 and -2 row 1 plus row 3. So I'm going to do these 2 row operations to clear out this column below the 3. So that should give me -2 times 7 minus 4 is 10. And -2, that should be 4. And then lastly, we'll do 5 row 2 plus row 3. So here we can verify that this matrix U is in fact a row echelon form of A. Next, we can verify that L times U actually equals A. Well, going across this first row, notice I just get the first row back. Going across the second row, so matching up this second row with each of these columns, well, first off, I'm going to get -3. Then I get 7 minus 2 is 5. Then I get 2 minus 1 is 1. Next, I get 6. 2, -5, 1 matched up with 7, -2 gives me -4. And lastly, if I match up 2, -5, 1 with -2, -1, 1, -1, I get 0. And so sure enough, L times U is equal to A. And so these 2 matrices, L and U, do in fact give an LU factorization of A. So I thought it would be nice just to check, to verify, and to kind of see what's going on here, right? So the product of these 2 matrices gives me A, and I can row reduce A to get U. So this isn't necessarily how to find one. I just wanted to sort of verify that this was in fact an LU factorization, and I wanted to give some intuition as to sort of how these matrices work together. So why do we use LU factorizations? So we'll say question 1. Many of you might be asking, why? answer 1. Well, actually, there's only one answer to question 1. But so let's suppose we wanted to solve many matrix equations with different vectors b, but the same matrix A. And so AX equals B1, AX equals B2, and so on. Now, we've of course gone over many, many ways of doing this so far. We can set up an augmented matrix and row reduce. We can, if A is invertible, right, we can calculate the inverse of A and solve all these by just multiplying both sides of each of these equations by A inverse. So the first way of row reducing each time is very lengthy in like a single setting, right? We have to do many row operations and we have to keep track of a lot of numbers. And so doing many row operations takes time and leads to many mistakes. Right, the more, I guess, arithmetic operations you have to do, the more likely you are to make an arithmetic error somewhere. Also, so, you know, maybe solving it using the inverse method by multiplying each side by the inverse of A, well, finding the inverse can be hard, as we've seen, and sometimes the inverse doesn't even exist. So what we're going to see is that being able to factorize A as an LU factorization will give an efficient way to solve each of these matrix equations. So an LU factorization gives an efficient way to solve each equation. And so this is very useful because oftentimes in applications of linear algebra, you do want to be able to solve multiple different matrix equations like this. And so especially if you're going to be ever, you know, programming an algorithm to do so, which is highly likely if you're applying linear algebra, this provides also, I think, a very efficient way to program a computer to solve many matrix equations. So all I want to do today, or to end this lecture, is give an algorithm for how we would do so with an LU factorization, so how we would solve a matrix equation like this using LU, and then solve it. And so what's going to be kind of funny about this is that you'll see that doing this once is actually a relatively inefficient way to solve a matrix equation. But as I'm going, I'll explain why potentially doing it many times, or if we had to solve many matrix equations, eventually it would prove to be efficient. So let's let B equal the following vector. And we want to solve AX equals B. So, how to do so using an LU factorization. So notice, I'll put the algorithm here in the right side, how to use A equals LU to solve AX equals B. So notice this equation, AX equals B, is equivalent, well, I can just replace A by its factorization LU. Right, so if AX equals B, then LU times X equals B. And that's just because we've assumed A is equal to L times U. Well, so this implies I can rearrange these parentheses by my matrix operations rules and get that L times U times X is equal to B. Well, U times X here is just a vector of length M. And so I can let Ux equal a vector Y, where Y is in Rm. And so what I'm doing, notice X is still variable, right? We don't know the value of X. We're just sort of assigning this new vector of variables Y. And so then what we can do is we can solve L times Y is equal to B, right? Basically, we just let Ux equal this new vector Y, and we solve the matrix equation Ly equals B. And we'll see in a second why this proves to be a very efficient solution, sort of given the nature of L. Well, once we have the value of Y that gives a solution here, we can solve Ux equals Y. But notice, if we solve for this vector X and work our way back up, X gives a solution to Ax equals B. So X is a solution to Ax equals B. And so why LU factorizations? Well, it turns out that these steps 3 and 4 are very efficient. So what I want to do is use sort of this algorithm to, in this example, in order to solve this matrix equation, and then we will wrap up for today. So how do we actually use this algorithm? We don't really do much with steps 1 and 2. Steps 1 and 2 just justify why steps 3 and 4 are acceptable for solving. So first thing we do is we solve Ly equals B. And so here Y is a vector in R3. And so notice we can solve Ly equals B because L is a 3 by 3 matrix, B is a vector of length 3. And so notice that given the makeup of L, I get the following equations in this matrix equation. So I get y1 equal to -7, negative y1 plus y2 equals 5, and 2y1 plus minus 5y2 plus y3 equals 2. So this would be very easy to solve using a small number of row reduction steps. So notice, if I set up the augmented matrix for this matrix equation, I get 1, 0, 0, -7, 5, -1, 1, 0, 5, and 2, -5, 1, 2. And so what I can do now is use 3 row reduction steps. So first I'm going to clear out here below. So -2 row 1 plus row 3, that should give me 16. And of course I should have a -5 here. And so now I do one more row reduction step. I do 5 row 2 plus row 3. And I get the matrix 1, 0, -2, 0, 0, 1. And so then that would be 6. And so notice I've now found my vector y in a very efficient manner using only 3 row reduction steps. All right, so this is number 3. I've solved L times y equals b. So now I want to use this newly found vector y, which is equal to -7, -2, 6, in order to solve for the vector x in step 4. And so now what I'm going to do is solve the matrix equation u times x equals y. And so notice now I'm going to use this vector y as my solution vector. So if I were to set up the augmented matrix, I would get the following. And again, because U is a row echelon form, I only have to do the row reduction steps where I clear in the rows above, and this won't take too many steps. So first off, I'm going to use this -1 to clear row 3 and row 2. Or sorry, row 2 and row 1. So here I get a 0. Here I'm doing -2 times 6 is -12 plus -7 is -19. Here I get 0, -2, -1. And so here -6 plus -2 is, or sorry, that should be a 0, -8, 0, 0, -1, 6. And so now I'm going to divide row 2 by -2 and divide row 3 by -1, or multiply row 3 by -1 to get the following matrix. And now I'm going to use row 2 to clear out row 1. So that should be +9. And that gives me my reduced matrix. So last few steps here to here, I did make a small mistake that I corrected and didn't say anything about. I divided row 2 through by -2. Then I divided row 3 through by -1. Then I added 7 row 2 plus row 1. And then I finished off the row reduction by dividing row 1 by 3. And so notice this gives me a solution vector x, which turns out to be a solution to ax equals b. So what I'm going to do now, just to write it out fully, I'll erase the algorithm. So this corresponds to a solution vector x equals 3, 4, -6, which is a solution to ax equals b. And so note here, as a single sort of time through solving this, the LU factorization was definitely a little longer than had we just row reduced normally. But notice each sequence of steps it took to row reduce L and U was a very straightforward sequence, and in the long run would end up taking a little less time than if I started with A and had to do the full row reduction every time to solve AX equals B. And so, granted, solving this matrix when U is already in a row echelon form is a lot shorter than starting with A and having to row reduce it all the way. So, as a single method of solving AX equals B, it tends to be a little longer. If you were to have to solve many, many matrix equations similar to this, it would end up being a shorter method of solution. So next video, we're going to discuss how to actually find an LU factorization, and then we'll look at one more example.